What are some practical applications of rotational motion in the field of engineering? One example is in the design of processing plants, where principles of rotational motion are fundamental. So before we can get to this, a process flow sheet similar to this should first be carefully planned and optimized according to its primary purpose. In the case of this mineral processing plant, our primary purpose is to turn mineral rocks to gold bars. Such use of rotational motion principles in milling machines is important to induce material breakage or size reduction. This is widely used even in other industry applications. For example, in milling food grains to reduce its size to form flour, which is later processed to produce pasta. Another example, in milling potassium feldspar lumps to reduce its size to form feldspar powder, which is later processed to produce our very own ceramics. These initial steps require milling machines. In order to produce the desired product, certain variables may control the forces, that is, impact, compressive, and abrasive forces, involved during the process. What is fascinating is that no matter how complex the operations may appear, optimal operating conditions for milling machines are simply based on fundamental physics. One operating condition of central importance is critical speed. The critical speed of the milling machines may vary according to its diameter. Hence, the famous equation of critical speed is used in a lot of applications and is found to be equal to 42.3 times the quantity of d raised to negative 0.5, where d is the mill effective inside diameter in meters, while critical speed is in units of revolutions per minute. To simplify our discussion and derivation, let us take a snapshot of the mill's rotational motion and let our entire bulk material be represented by a red point particle. During motion, the force pulling the red point particle to the center of the mill is the component of its weight. Therefore, we find that centripetal force is equal to the product of the red point particle's mass times the constant acceleration due to gravity, or simply g, times cosine of angle alpha as shown in the diagram. Now, for it to stay at the circumference, it needs to be counteracted by a force opposite of its direction, which is referred to as a centrifugal force. There are two ways how the red point particle may move as the milling machine rotates. It may cascade or centrifuge. At this point, if you want to use this as an example to your students, you may ask them to think critically and analyze based on the purposes of the milling machine as described in the examples earlier. You may ask them whether, do we want the particle to cascade or centrifuge? The answer, we want our material to cascade and not to centrifuge. Otherwise, the material will simply stick along the milling machine's inner shell without experiencing any form of breakage or size reduction. If it simply sticks, such a waste of energy, isn't it? So how does this translate to our calculations? To start, we equate centripetal force to centrifugal force. Going back to our diagram, if big R is the radius of the milling machine and R sub s is the radius of the red point particle, then the difference between the two can be represented by small r, where small r, or simply call it r, when multiplied to the angular velocity squared, would give us radial acceleration, which is also equal to the tangential velocity squared over r. We have described centripetal force previously, and from the theoretical discussion of rotational motion, we learned that centrifugal force is equal to the product of mass times radial acceleration. Cancelling m on both sides, we are left with g cosine alpha equal to radial acceleration, which is in turn equal to the product of radius r and the angular acceleration squared. Since r was set as a difference between big R and r sub s, and now introducing an alternate equation of angular velocity in terms of frequency, the equation can be rewritten as follows. from this point forward will all be mathematics. That would eventually lead us back to the equation for critical speed as defined earlier. For your reference, the complete solution will be provided as part of the additional resources of this module, Module 1. Therefore, through this application, we have just demonstrated to our students that the mechanisms of what appears to be complex technology can actually be explained by understanding the physics behind it.